In today's section, we're going to take a look at graphs of rational functions. A rational function is the quotient of two polynomial functions and has the form f of x equals g of x over h of x. So basically, it's a fractional function. So remember, rational numbers, anything that can be expressed as a fraction. Now, the domain of a rational function, so that's all possible x values. This can only be found by setting the denominator equal to 0. Because you cannot divide by 0, this creates a vertical asymptote. So let's take a look at a couple examples. In the first one here, x over x squared minus 25, I need to factor the denominator. So I'm going to put the product of the first and last, so negative 25 in the top, then the middle term of 0 in the bottom. And I come up with 5 and negative 5. So those are my two factors, x plus 5 and x minus 5. So the domain restrictions here is the set of x such that x cannot equal (5) or negative 5. Both of those would create a 0 in the denominator, and you will see vertical asymptotes if you graph in your calculator. Second one here, I'm going to go ahead and factor out the x. And I'm going to factor out the binomial there, or the quadratic rather. So I get x times x minus 4 times x minus 1. So again, my domain restrictions are going to be anything that makes that 0. So it's x plus 2 over the denominator of x times x minus 4 times x minus 1. And again, I know that x cannot be equal to, so it's a set of x such that x cannot equal 0, 4, or 1. And that's all we're looking to do. When will the denominator equal 0? Now, a rational function in lowest terms is simply a rational function then the top and bottom have no common factors. So once you factor them out, you've removed the common factors. It's just like reducing, simplifying the term, just like simplifying fractions. So if I look at this first example, I'll go ahead and factor the top, product of the first and last, middle term and the bottom, find factors at the top that add to the bottom. So I get x minus 4, x plus 2. And in the denominator, let's see. Actually, it looks like there's a 2 in common in all those terms. So I'm going to go ahead and factor out a 2 first. So it would be 2 times x squared plus x minus 20. And then I'll factor what's in the parentheses, so negative 20, 1. So I'm looking at 4 and 5. One of them has to be negative, so it must be a minus 4. So I go ahead and rewrite that, and I see x minus 4 is a common term in both the numerator and the denominator, so I can cancel that out and rewrite. Now when you graph this, that will still play a factor. That will create a hole, or a domain restriction. So there's still a restriction at positive 4 because that is in the denominator. Even though we can factor it out to produce the same graph, there is still that domain restriction. So it does create a hole. So when I write the domain, x cannot equal negative 5 or 4. So when I write that out, negative 5 or 4. Now again, this one's already been factored out to us, for us rather, and we see that x plus 2 is common in both numerator and denominator, so I could reduce those. However, that does still leave me with a domain restriction that creates a hole in the graph, not an asymptote, but a hole. So x cannot equal -2, 3, -4, 5, and 7. Now, vertical asymptotes. The line x equals a is a variable, is a vertical asymptote for f of x if f of x approaches infinity or f of x approaches negative infinity as x approaches a. So what that means is it's going to get infinitely closer and closer and closer, you see in the graphs here, to that value, but it will never actually touch or cross it. So we have vertical asymptotes here on this graph at -2. Let me change the line here to a dashed line. And at -1. So this graph gets very, very close, but never quite touches. Then we see one over here on this graph at 2. So again, vertical asymptotes, x equals -2, x equals -1, and x equals 2. Now when I want to find those algebraically, very simple. We've already seen, you factor and find zeros in the denominator. So again, let's factor some of these and take a look at the vertical asymptotes. So all I'm concerned about right now is the denominator. X squared minus 25 is the difference of squares, so it ends up being 4x over x plus 5, x minus 5. So I will see vertical asymptotes at x equals -5 and x equals 5. And in this, q of x equals x plus 6 over x squared plus 5. I factor again, or I look to factor the denominator. It doesn't appear to be factorable. And so I'll go ahead and just set it equal to 0. Do a little rearranging. So I subtract 5 from both sides. X squared equals -5. Square root it, and x equals square root of -5. So I see this has imaginary values. So this one will not have any vertical asymptotes because of these imaginary values. So the domain restriction here is imaginary, so there are no vertical asymptotes created. We'll go ahead and graph this here just so that we can verify. If I use alpha y equals enter, plugs in the stacked fractions, x plus 6 over x squared plus 5. And we see we get this little blip, but there is no vertical asymptote. And next example here. I'll go ahead and factor the denominator. 12 over -8. Look for factor at the top, add to the bottom. Looks like 6 and 2. It's going to be -6 and a -2. Over x minus 6, x minus 2. And then I will see vertical asymptotes in a value that puts those at 0. So that would be at x equals 6 and at x equals 2. Now, horizontal and oblique or slant asymptotes, as they're sometimes called, look like this. We see a vertical one at this graph at 2, and we also see a horizontal one at 2 as well. And here we see a slant or oblique asymptote right there. Now, we don't know offhand what the equation of that line is because it's not as easy of a linear equation. So we've got horizontal, and we've got the slant or oblique. So in order to find those proper rational functions where the degree on top is less than 1 degree on the bottom, That's what's considered proper, just like an improper fraction. So here's a quick little chart. I would go ahead and definitely mark this for your notes of when we're looking at these different types of asymptotes. So in that first example, you see it's less than, so as your bottom gets approaching infinity, it becomes approaching 0. The second is when they're equal. You're really just looking at the ratio of the terms. When it's 1 greater, we're going to use our polynomial long division that creates slant or oblique asymptotes. And if it's more than 1, there is no vertical asymptote, or slant asymptote rather. So again, here's the complex one, uses polynomial long division in order to determine the oblique or slant asymptote. And we'll see what that looks like here. So again, first thing I do when I approach the problem is I look at the degree of the polynomial. I see I have 16x cubed on top and x squared on the bottom, so the top is 1 degree greater. Now, the fact that it's 1 degree greater tells me I'm going to have a slant or oblique asymptote. So I need to use polynomial long division. Good thing is we're just looking for the equation of a line, so we really don't care about the remainder when we're using polynomial long division. So I'm going to go ahead and set this up. So 8x squared into 16x cubed, that goes into 2x. Then I multiply by each term, and it's just like long division. We're going to go ahead and subtract those, so I get 16x cubed minus 14x squared plus 2x. So then we're going to go ahead and subtract these. Set a nice bar here, clean it up a little bit. So those cancel. I'm left with minus a minus. And then we're going to go ahead and multiply again. This one's going to be a 7/4. 7/4 x is 56/4, which reduces down to a 14. So that will give me my 14x squared, leaving with 49 over 4x. Now the remainder here is not really important because I've got my equation 2x plus 7/4. That's my linear equation of the oblique or slant asymptote. And this is my remainder when I finish the subtraction. So again, let's go ahead and pull up a calculator here and we'll take a look at what this looks like. So we'll go ahead and graph the rational function. We'll just alter this here, 16x cubed minus 2. Oh, let me delete this. Over minus 2. And then denominator 8. And x squared minus 7x plus 1. And then for my second equation here, we'll take a quick look at what this looks like. So I see clearly there is an oblique asymptote. And I'll go ahead and graph my new function, 2x plus 7/4. I'll just use parentheses here for the 7 divided by 4. We'll take a look. And there we go. So let's go look at another example here. And here I have 9x to the fourth plus 8x cubed minus 7 over x squared minus 4. So the first thing I look at is the degree of the polynomial. I see it's 2 greater, so it's more than 1 greater, which means there is no horizontal or oblique asymptote. Now I do still want to find vertical asymptotes, which this does have anytime the denominator can set equal to 0. So I'm going to factor it out. Again, this is the difference of squares, x minus 2, x plus 2. So this will have vertical asymptotes at 2 and negative 2. Okay, so that's really all there is to rational functions. Bring any questions with you tomorrow. We'll get a little more practice.